All right. So this is a demonstration of Boyle's law, which for Chem 103 is lab exercise number 4. Can be found in Blackboard. And this video will accompany all the other documents as soon as it is completed and uploaded. This is what the document looks like for the student. Boyle's law is a study of pressure versus volume of a gas, and in particular, an ideal gas. All right. The description of Boyle's law, we could take just a couple of minutes to describe Boyle's experiment. Boyle wanted to know the relationship between pressure on a gas and its volume. So he devised an instrument called a J-tube. This is also repeated in the lecture. And what he did was, let's give it a little more volume here. In that J-tube, he added mercury, which is a liquid. And as he added mercury, it pooled in the bottom, and eventually it touched the inside of the J, which essentially trapped the gas inside this part of the J-tube. And as he added more, he noticed that the more he added on this side, the less it moved on this side. So what he concluded was that the gas inside was pushing back with a force with a force that was equal to this amount here. So this represented an expression of pressure in terms of the height of the column of mercury. So he conducted this experiment at constant temperature and constant moles of gas, because once you trap the gas, can't put any more in there, right? So you'll remember from our discussion of gases that 4 parameters describe a gas: pressure, volume, temperature, and how much of it there is, number of moles. So if you hold these 2 constant, then you can study the relationship of pressure and volume. So that's what we're going to do also, except we're going to use a modified version. All right, and I'll show you the apparatus right now. Okay, this is the apparatus we're going to use. We're going to have an enclosed vessel which provides external pressure on a trapped gas. So how do we trap the gas? We use a syringe. And these are not your typical syringes, because the seal at the end of the plunger doesn't provide as so much friction as you would normally see in one of these plastic syringes. So it behaves better, it behaves more ideally. Okay, so what do? Well, in order to start the experiment, we start from a volume. And normally what you would do is set it at 10 milliliters. But what happens is, when the pressure is finally released completely, the volume is less than 10 milliliters. So we could go a little bit higher. Don't want to go too far, because the last measurement we don't want beyond 10, then we can't read it. So we'll set it there. And how do we trap the gas? Well, I use a cork that's been bored only a little bit on one side. Now, there's our trapped gas. So we insert that into the pop bottle, and these pop bottles are one experiment only. Once we get finished with this experiment, that pop bottle goes in the trash. because it's been under a lot of stress and the risk in future experiments of explosion is too high. So they're cheap, disposable. We use them for one experiment and that's it. So we put the syringe in here. There we go. And then we seal it in such a way that we can add pressure. So I've created these little valve caps. And this valve stem ought to look familiar. It's the same one that's on many people's tires and their wheels. Okay, sealed up. Now we can add air to the surroundings and increase the pressure on the inside. So how do we know what the pressure is on the inside? Well, we use a tire gauge, which means when we read the tire gauge, the values that we obtain from the reading are in terms of pounds per square inch, PSI. And we need 3 of them for different ranges. They don't make one tire gauge that'll do the entire experiment for us. This one's a medium, this one's a low, and this one should be a high. Yeah, I got them marked on the ends here. All right. So what do we do next? Well, instead of adding pressure and then measuring it each time we add pressure, we're going to add pressure till we get up to maybe 60 pounds or so. Then we're going to measure the pressure as we release it. Right? It's kind of like taking your blood pressure. They pressurize the cuff on your arm, and then they measure the blood pressure by releasing the pressure slowly. So we're going to use that model. Okay, how do I pressurize it? Well, you could use a tire pump, a hand pump, or a foot pump, but I'm lazy. So I'm going to use my emergency tire pump that I use on my vehicle. And here's a portable battery. Here's my pump. And I'm just going to hook it up to this container and pressurize it. Now, the other advantage to this is I can start the pressurization process and step back from it. In case it does explode, then I'll be out of harm's way. So here we go. Let's see, we're up to about 58 pounds, and the volume is dropped from about 10 to in the neighborhood of 5432. Let's go down just a little bit more. And that's the advantage of using a system. If I detect a problem, I can always cut power from here rather than down there. Okay, that's enough pressure. We're up to about 60 pounds. Now this gauge is rough, right? We need a tire gauge to give us exact measure. And if you were here in person, you can see the condensation in there, but there's a lot of heat as well. So we need to let it sit for just a few minutes so the temperature will equilibrate. So as we check the pressure, the temperature remains as near constant as possible. The only way to maintain the pressure, the temperature, within a very narrow range is to provide some sort of a bath. And I suspect that Boyle might have used something like an ice bath, or use, well, in those days, in Boyle's day, houses were made of masonry. So their temperatures were very stable throughout the year. So he might not have needed something as elaborate as an ice bath. Back to the topic. Okay, so we've got the pressure built up. We need to remove this, and you may hear some hissing. There we go. Now, when do we want to measure the pressure and check the volume? Because over here, you'll see I've set up a table where we have the gauge pressure measured by the tire gauge and the volume associated with it. So which do you measure first, the volume or the pressure? Well, think about it. If you measured the volume first and then took the pressure, what happens when you take a tire's pressure? When you press that gauge on the valve, you hear a ch, ch. You're losing some air. So that means the pressure is not actually all being applied. So if you measure the volume first, it's going to change when you measure the pressure afterwards. So we measure the pressure first, allowing that for that escape, then we measure the volume. Okay, so that's what we're going to do next. We're going to start with a high, right? The high pressure, and everybody knows how to use a gauge. You be sure that the plunger or the gauge is set, is pushed to its bottom. Then you position it over the valve and press straight down. And we have a pressure reading, which in this case is, let's see, each one of these tick marks between the major marks is 2 psi. So it looks like we have 2, 4, 6, 8, 52, 4, 6, 7, 57 psi. We have 57 psi as our first measure. Now we're going to check the volume. I always swirl it around because sometimes that gasket, that seal, sticks. So we want to encourage it to release. Then we rotate it around to where we can see the dial. Now what you need to do is check your measurement on the same side of that black ring as possible. So I'm going to go to the left side, or the gas side, and that's the side I'm going to read every time. Okay, it looks like we're up to 1.6 milliliters. 1.6 milliliters at 57 psi. Okay. Now let's do it again. What we want to do is have 10 or so at least readings. So we probably don't want to go too far past 50 psi. It'd probably be better to judge it by the volume obtained. So each one of these has a nipple on the back, and that's what you use to let the air out of your neighbor's tire when his dog craps on your lawn. So do that. I see the plunger moving. Okay, that's good. swirl it around. Now we're going to actually take the measure. Okay, this one's down to 43.5. And the volume then is, let's see, about 2.3 milliliters. Remember that last digit is a guess. Okay? And we just keep doing that until there's no more pressure coming out. Let's let a little bit out and watch the plunger. Let's do it again. Now, when do you know when to switch? Well, you want to use the most accurate one possible. So you look at the next one, which is going to be more accurate. The mid-range is more accurate than the high range. And you can pick this one up in the neighborhood of the high to mid-40s, right? So my guess is that since the last one was 43.5, this one's going to be well within the range of the medium and give you a more accurate reading. So we're going to switch to the medium now. Okay. All right, PSI. Each one of these tick marks is 1 PSI. So there's 35, 36, right on the money. 36 PSI. Okay. Now, what volume does that represent? What is associated with that volume? I see 2.6 milliliters. 2.6 milliliters. Okay. We're still within the range of the medium, because the medium goes on down to 10 psi. So let's let some more air out. All right. And measure the pressure, which is now 25 and a half. 25 and a half PSI. Now, what volume is associated with that number? Notice, for those of you who recall your courses in mathematics, these are number pairs, like x, y, that you could graph on a graph as in a Cartesian system, where you have two axes together. One axis for this one axis for that one, and you follow one up, and you follow the other one out, and where they meet, that's your point. So this is a point, a point, a point, another point on our graph. We just need the volume in this case. All right. That looks like 3.4. 3.4 milliliters. All right, 25 and a half. Let's see what the low range is set for. Low range kicks in at 20 psi. So we'll get another one, at least another one, out of the mid-range. Let's let some more air out. And take the pressure measurement. All right, now we have 15, 16, 17, 18 on the money. 18 psi. Okay, and what volume do we have? Okay, 4.3. 4.3 milliliters. Notice as the pressure decreases, the volume increases. What does that say? Well, without getting too particular, that means that these two variables are inversely related. As one goes down, the other one goes up, or vice versa. Pressure goes up, volume goes down. It's an inverse relationship. Now I think we can switch to the low range and let some more air out. Okay, let's take the pressure. And it looks like we have, each one of these tick marks is a half. So that looks like 8. That's 8.5, 8.8. 8.8 PSI. So it went down quite a bit with that last one. See what volume that represents. Let's see, it looks like we're sitting right on 5.7. 5.7 milliliters. Okay, let some more out. And check the pressure. Pressure is now at 3.1. 3.1 PSI. And the volume is, looks like 7.4 milliliters. 0.4. Okay, we don't have much more room to play with in this pressure thing. See if we can even get a measurement out of it. Nope. I went too far. All right. So for our last measurement, we need 0 gauge pressure. Just because I couldn't read it on the gauge doesn't mean it's 0. So in order to be 0, we need to have the pressure so low that we can remove the cap, and now it's at atmospheric pressure. All right. So we remove the cap, and that's our 0 gauge pressure now. What volume is that? Okay, we've got, okay, it's not quite back to 10. It's about 9.8. 9.8 milliliters at 0 gauge pressure. All right, now here comes the fun part. This is the gauge pressure, but remember these gauges are, they experience 2 types of pressure. They experience the pressure from within the nipple and the pressure on the outside of the plunger, right? So the gauge pressure is actually, needs to be, for the total pressure inside the vessel, we need to add that extra bit of pressure that's pushing on this side of the piston, right? So in order to do that, we need to know what's the barometric pressure. How much pressure is actually pushing on the outside of that plunger and on the outside of the container. And we do that by checking our barometer on the wall over there. And that pressure, now I better check, that was measured several minutes ago. Let's see if it's changed. 2752, 2749. So we need to change that. Pressure has gone down. So what does that mean? That means we got bad weather on the way, right? Anybody who knows how to read a barometer. There. Now, to measure the total pressure, you can't add two numbers that have different units. This one has PSI units. This one has inches of mercury unit of pressure. You can't add them together. So convert each one of them to atmospheres. Convert this to atmospheres. Convert that to atmospheres. I'll do this one for you. 27.49 inches of mercury. And we want that to be in terms of atmospheres, right? Right. So we need to cancel inches of mercury down here and end up with atmospheres there. So what's the conversion factor? How many atmospheres equals inches of mercury? Well, one atmosphere is 29.92 inches of mercury. So divide 2992 into 2749. And I'm not good enough to do that in my head. And I don't feel like longhand division. So let's use a calculator. Okay, my marker again. So this value is 0.9, see, 4 significant figures, 188 atmospheres. That's the barometric pressure that has to be added to each one of the gauge pressures. But now these have to be converted to atmospheres before you can add this one, right? So how do you convert this one? What's the equivalence for PSI? Well, the procedure has it for you, but I'll tell you right now. To convert PSI to atmospheres, and then add this atmospheres for your total, you need 14.69 PSI per, let's see, let's put it on top, 1 atmosphere. That's your multiplier, which in fact is a divisor. 14.69 divided into each one of these will give you the gauge pressure in atmospheres. Then you add to each one of those this, and that gives you that number. All right? So you fill the chart in yourself. I just told you how to do it. Now, what do you get when you plot pressure and volume? Well, Boyle told us what you get, right? If you plot pressure against volume, you get an inverse relationship, which means the slope is this direction. Direct relationships are that way, inverse are this way. But since P times V equals a constant, then as this one goes up, that one goes down, and it always gives you a hyperbola. Scientists hate curves. Whenever we can get a straight line, we go for it. So we were going to convert to make this into a straight line. Well, how does that work? Well, what do you need to be a straight line? You need y equals mx plus b. Right? So you need the slope of your straight line here, and then you need your variables there. So this slope is a constant. There's your constant. That's your m. So how do we arrange this to put m times one of the factors? Well, do it this way. What if we brought v over on this side? What would that do? Well, if you brought it from here to here, it makes the inverse, right? Because you're dividing by v. Times v, divide by v. Now you have y equals mx. Plus b is 0. So now if you plot it, pressure against 1 over volume, and the units of measure here, since volume is in milliliters, 1 over V is milliliters to the -1. So when you give me your plots in your report, that's the unit of measure, the inverse milliliters, or to the -1. And this is going to be atmospheres, of course. This will be milliliters. Atmospheres still, we didn't change that one. Now when you plot it, you'll get a straight line. Okay, that's what that's all about. One other calculation that the printed method wants you to do is multiply these two together and give you a value. That value is going to hover around a constant, which is this one. Multiply them together, you should get a constant. It won't be exact because of experimental error, but it will be very close. And if you average them together, you'll get a good estimate of what K should be. All right. Now, let me look at the method and see if there's anything else I've missed. Okay. All right, you have some questions to answer, and answering the questions will also, some of the questions that occur in these methods you've already answered in the structure of your report. If you answer the question someplace else in the report, when you get to the question section, just reference that part of the report that gives the answer. You don't have to write the answer out all over again. Just tell me where it is, okay? And then you can get credit for it. All right, so that's Boyle's law, and that's all you're going to need to do this experiment. It's a very simple experiment, very straightforward, no surprises. Safety, you want to consider safety. So when you do this experiment, what are your safety considerations? Well, primarily is increased pressure inside a container, right? Inside this vessel, the pressure went up to 60 psi. Now these bottles are made out of PETE, and there's a question about that in the document. And the way it's constructed, these vessels are supposed to be good to 100 psi. So we were well within limits, but it's been stressed once, contracted, stressed again. If we do it again, it's stressed again, and too many stresses will cause an explosion or catastrophic failure. That's what happens to airliners when they go up to 35,000 feet and then come back down to 1 atmosphere and go back up, come back down, and go back up. The plane goes like this, so many times, and eventually it develops a catastrophic crack. So that's why planes, after so many flights, are required by the FAA to undergo inspections for stress cracks that would occur from that. And that's why airplanes that go up, jets that go up that high, do not pressurize the cabin at 1 atmosphere. They pressurize it at maybe 5,000 or 6,000 feet, or maybe even more, just so that it limits the stress on the airframe. Okay, so that one's done. The report is up to you, and we're finished.